लास्ट वीडियो में हमने चार्जिंग ऑफ द मेटेलिक बॉडी देखा था। वापस इसको आप स्लाइड के थ्रू देख लीजिए। you can read it and you can understand it how the given charge is uniformly distributed. Now we are understanding very important phenomena by the animation. Animation is that a charge given to any conducting body always sits on the outer surface, and inside the conducting body no charge. All of you just go through this video and try to understand.
Demonstrates a bunch of electrostatic stuff with soap bubbles. Start by finding a very smooth surface. The smoother the better. The smoother surface helps the bubble keep its shape. I'm using this laminated tabletop. Next, mix up some dishwashing soap and water. Lastly, get a drinking straw. To blow a large bubble, suck some soap into the straw, but not into your mouth, and then blow it gently onto the smooth surface. The surface needs to be coated in soapy water to form the bottom of the bubble. Now for the real fun. We need an electrically charged object. We can use the triboelectric effect to charge a variety of different things. Try rubbing a balloon or plastic Coke bottle against your hair to charge the balloon or Coke bottle. A lot of different things will work. See my video about the triboelectric effect for tips on this. Bring the side of the object that you charged near the soap bubble. The soap bubble is attracted to the charged object. If you come too close, it'll burst. Have fun pulling the soap bubble around or making it change its shape. Next, blow a smaller bubble in the center of the bigger one. Notice that when you attract the bigger one around, the smaller one doesn't move. Why not? Here's an explanation for all this. When you charge up an object, depending on the material you used, the area you charged either has more positive protons than negative electrons, like this glass, or more negative electrons than positive protons, like our plastic bottle. For our bottle, we say it's negatively charged. The soap bubble overall is electrically neutral. It has an equal number of positive protons and negative electrons. But it does contain impurities such as metals that are ions, i.e. they're charged either negatively or positively, and the skin of the bubble itself is charged. So while overall the bubble is neutral, the charge within it can move around, like with a metal object. With the soap bubble shown here, when you bring a negatively charged object close to the bubble, the negative electrons on the object attract the positively charged ions within the bubble, even some from the other side. That's because opposite charges attract each other. Now you have one side of the bubble with more negative charges than positive. We say it's negatively charged. And the other side has more positive charges than negative. We say it's positively charged. And just as like charges repel each other, opposite charges attract each other. So the negatively charged bottle attracts a now positively charged side of the bubble. It also still repels a negatively charged side of the bubble, but that's further away, so that repulsion is weaker. The attraction between the negatively charged bottle and the positively charged side of the bubble is stronger and wins. The bubble moves towards the bottle. And what about our smaller bubble that didn't move? It wasn't attracted because it's inside the bigger bubble, and the bigger bubble is acting like an electrically conductive container. It's a Faraday cage, which is the same as saying it's experiencing the Faraday ice pail effect. The Faraday cage protects objects inside it from external electric effects. It's the same thing that happens when lightning hits a plane. The passengers don't get shocked because the metal plane is a Faraday cage. The lightning affects the outer electrically conductive surface of the plane, but nothing inside. Another example is a dome on the top of a Van de Graaff generator. It's also a Faraday cage. So the soap bubble inside doesn't experience any attraction or repulsion of charge at all. Well, thanks for watching.